Hi, my name is Bia Stella, and I'm going to be taking you through the explainable AI techniques for contrastive knowledge distillation for banana leaf disease diagnosis using sparse capsule networks. First off, we have to know the purpose of the explainable AI. The first one is it enables us to understand the model decision making and helps to improve trust and adoption by farmers and researchers, then helps to diagnose the model performance, then enhances prevention and treatment recommendations. We have three explainable AI techniques that we applied, and the first one is GradCam, silencing maps, and then the counterfactual explanations. I'll be taking you through the details of each of these AI techniques that we used. The models that we selected, there were four models. The best performing models were the MobileNet V2 and the CNN model. And then the worst performing models were the ResNet and the EfficientNet models. The details of the GradCam. GradCam is used to generate heat maps, which visualize which leaf areas influence the model's prediction. And this is how it works. It performs a forward pass to get the output and activations from the model. Let's head straight to the results that we got from the GradCam. Well, the first one here is a leaf that is from the class Xanthomonas, and the Xanthomonas leaves are the characteristics of these leaves are that they are yellowish and have some brown patterns on them. And as we can see for the GradCam, it shows it highlights the areas that the model focuses on the most, and the red and yellow patterns show that where the models focus the most, and then the bluish focus on the areas that are not so important when the model is identifying the class Xanthomonas. And as we can see, the yellow and red are on the leaf. Then this image is for the class healthy. As you can see, the leaf is completely green. And we can see that from the results, the yellow and the red patterns are mostly on the leaf. For the characteristics of a healthy leaf, of course, it has to be purely green, uniform green leaves, and the red and yellow patterns were mostly on the green part of the leaf and the smooth areas. As we can see for the Xanthomonas leaf, it's not that smooth compared to the healthy leaf. Then we have the class Segatoka. Segatoka, the characteristics of this class is that there's yellowish patterns on the leaves, then irregular spots, and discoloration, as we can see here. And our GradCam, highlights the yellowish spots that are on this leaf, as we can see from these red and yellowish markings. And these results were for the class MobileNet. For the MobileNet model. And then these are the results for the for the CNN model. It's similar to the results of the MobileNet model, because as we can see, the yellowish and the yellow and the red red streaks were mostly on the leaf, the major focus on where. And then we go to the saliency map. The saliency map is used to understand which pixels contribute most to the classification of the images. It's generated by calculating the gradient of the model's output with respect to the input image. Let's go straight to the outputs. of the saliency map. Okay, here we have the class Xanthomonas as well. The salience, the red spots were mostly on the brown patterns that were on this leaf. And these features highlight or show that the leaf is infected by the bacteria Xanthomonas, as we can see here. And then the second image is for a leaf that has Segatoka. And the red spots on the saliency map mostly highlight the yellowish spots that are on the leaf. And then the third image here is a leaf that is from the class Healthy. You can see that the red spots were mostly on the part of the leaf that were smooth and green. This saliency map is for the model, for the MobileNet model, and then these saliency map results are for the CNN model. Then we have the last XAI tool, and that's the counterfactual explanation. Well, the counterfactual explanations are used to explore how many changes would affect the model's prediction. Essentially, it finds the smallest change required to alter the model's prediction. Heading straight to the results that we got. Well, these are the results for the MobileNet model. Well, this class 1 is class Segatoka, the original image. But as we can see here on the counterfactual image, that they've added a few brown spots to the leaf. That makes it change to the class Xanthomonas, because the Xanthomonas leaf has like the brown spots. And then this second image is from the class Xanthomonas. The original image is from Xanthomonas. And then the counterfactual image, you can see that the green spots on this counterfactual image, which makes this image change to the class Segatoka. And then the last image is a healthy leaf. But as you can see on the counterfactual image, the yellowish spots, which alters the image to be a leaf from the class Segatoka. Well, these were the results for the MobileNet model. And then these are the results for the CNN model, and which are similar to the results that were from the MobileNet model. That's all I had. Thank you.
Hey guys, so I'm going to be continuing with the XAI implementation results for the two of our worst performing models. So I'm only going to do for one, which is EfficientNet, but the other of the worst performing model on which we performed the XAI was the ResNet 50 model. So these are the breadcrumb results for the EfficientNet model. And we can see these are the areas that are in red on all the leaf images that are shown in the breadcrumbs. The areas in red are the ones that the model based on predominantly to classify these images. And the blue areas are the ones the model didn't really focus on. So as we can see in these different areas, the model was focusing more on uniform coloration of the leaf and homogeneous texture of the leaf, while it wasn't focusing on the really important features like the yellowing of the leaf, the damaged edges, the edge structure of the leaf. Yeah. So then moving on, these are the saliency maps for the EfficientNet model. And the saliency maps show which pixels contributed most to the model's prediction. So these are the pixels that contributed most to the prediction of the efficient net model. When we put these images, these are the pixel level features that the model was able to extract, but we see they are not really clear because it was mostly focusing on the background elements and not on the leaf itself. So that's to show that it was not properly learning the features, and there was minimal activation of important areas like the lesions on the leaf on this Segatoka image, like the brown damaged edges. Then moving on, this is the counterfactual explanation for the efficient net model. So this image originally was from class 2, and that's how the model classified it with a probability of 0.38. And these are the features that the model based on to classify this image as a class 2 image. But this model, the counterfactual for this model, the target image, the target class for the image was supposed to be class 1, but then, and these are the changes the changes map that shows the areas that was supposed to be classified by the model for it to actually be class 1. It was actually class 1 originally, but the model classified it as a class 2 image, which was Segatoka, which was Xanthomonas, yet it's supposed to be a Segatoka. So these are the changes, the red areas are the changes that were added, and the blue was removed from those areas. These areas here in the changes heat map, and more red was added on these damaged areas so that the model could classify the image as Segatoka. Yeah, thank you. That's it.